Myself Punyamurthy from IIT Guwahati. I welcome you to IIT PAL program. In this class, we will study about alkynes. Alkynes are hydrocarbons that contain at least one carbon-carbon triple bond. Example, ethane, and they have general formula CnH2n minus 2. In the previous classes, we have seen about alkanes, alkenes. This is a saturated hydrocarbon, and if you look at this one, they have general formula CnH2n plus 2. Next, we have seen about alkenes. They are also unsaturated hydrocarbons, and they have at least one carbon-carbon double bond. They have general formula CnH2n, and if you compare these three hydrocarbons, alkynes have less number of hydrogen atoms. For example, in this case, you have 2 carbon, 6 hydrogen atoms. In this case, you have 4 hydrogen atoms. Here, only you have the 2 hydrogen atoms. So, they have general formula CnH2n minus 2. So, let us see the structure of the carbon-carbon triple bond. If you look at the orbital structure of this molecule, so this each carbon and this has 2 sp hybridized orbital, which involve the bond formation, and the overlapping of one sp orbital of this carbon with another sp hybridized orbital of this carbon leads to the formation of the sigma bond. So, out of the 2 sp hybridized orbital, one is involved the formation of carbon-carbon bond. The remaining sp hybridized orbital overlaps with this s orbital of hydrogen to form the carbon hydrogen sigma bond. Similarly, this sp hybridized orbital of this carbon can overlap with this hydrogen s orbital of hydrogen to form this carbon hydrogen sigma bond. There are 2 unhybridized p orbital, and one of this p orbital of this carbon, for example, this one, the unhybridized p orbital can overlap with the p orbital of this carbon. These 2 orbitals parallel and they can overlap side on approach, they can form the carbon the pi bond. So, overlapping of these 2 p orbitals, unhybridized p orbitals results the formation of this pi bond. there is one more unhybridized p orbital that is perpendicular to this orbital. So, this carbon hydrogen sigma bond all on the is a linear molecule, and perpendicular to that you have the p orbital, they overlap, then they make they result the formation of the bi bond. In perpendicular to that p orbital you have another p orbital. So, this can overlap with this orbital. This orbital can overlap with this one. So, if you look at this one, this is perpendicular to that 90 degree between these two orbitals, they can make another bi bond. So, if you look at this one, it has 3 sigma bonds, one carbon sigma bond, you have one carbon sigma bond and 2 carbon hydrogen sigma bond. In addition to that, you have 2 bi bonds. These bi bonds are formed by the overlapping of these 2 unhybridized p orbitals. So, if you look at it's like cylindrical, right? You have the top and bottom, you have the bi electron cloud. Similarly, this side you have the bi electron cloud, and like completely this molecule, and around that there is a bi electron cloud that makes this molecule as a linear. If you see the bond angle between this carbon bond and CH bond is 180 degree. The bond length is 1.2 Armstrong. The shorter than carbon double bond, carbon single bond, and this bond length is 1.09 Armstrong. This is a structure of alkyne, and we have taken ethane an example. We have seen the structure, and it involves the sp hybridized orbital of carbon overlaps with s orbital of hydrogen to give to form the carbon hydrogen sigma bond, and similarly this sp hybridized orbital of this carbon overlaps with this carbon sp hybridized orbital and head on approach to form the sigma bond. Now, let us look at the nomenclature and isomerism of alkynes. In the IUPAC system, the names of alkynes are derived from the corresponding alkanes by replacing the suffix ane with yne. For examples, the corresponding alkane is, this is IUPAC name of this molecule is alkyne. This is the first member of this alkyne series. IUPAC name of this alkyne is ethyne. The corresponding alkane is ethane. If you look at it, the suffix ane has been replaced by yne. Let us look at the next example. So, IUPAC name of this alkyne is propyne. The corresponding alkane is propane. So, the first two members of this series have only one structure, ethane, propane, ethene, propene, and ethine, propyne. When you go for next member, butane, there are two structures possible in the case of butane. You can look at this one, and this is called but 1-butane and 2-butane. This is the IUPAC name of these compounds, and this 1 and 2 refers the position of the triple bond present in this molecule. When you go for the next molecule, having molecular formula C5H8, there are three possible structures. There are three possible structures. So, these two compounds differ in their position of the double bonds. So, name of this compound is pent 2-pentane, and this one is pent 1-pentane, and this compound 3-methyl 1-butane. So, if you see these structures, these two are positional isomers. If you see here, the carbon-carbon triple bond present under different positions. In this case, present between the carbon 1 and 2, here between the carbon 2 and 3. Therefore, this relationship between these two compounds are called positional isomers. And similarly, in this case, the triple bond present between this carbon 1 and 2, here 2 and 3, these two are called positional isomers. And if you compare these two compounds, this is a linear, this is a branched one. The relationship between these two compounds is chain isomers. Similarly, between this and this chain isomers, because this is a linear, this is a branched one. This is about the isomerism. They have all, look at it, they have same molecular formula, but different structures. So, these are linear structures, and so they differ in the position of the triple bond, then they are called positional isomers. But when you compare with this one, then they are called chain isomers. This is a branched one, this is a linear one. So, next let us look at the preparation of alkynes. There are two common methods are used to prepare alkynes, and the first approach is the reaction of calcium carbide with water. When you treat calcium carbide with water, it can give acetylene, ethene, so the industry uses to prepare ethine by using this method, because this is one of the important alkynes because we widely use for ethine to make new organic compounds as well as to make materials, and this is very important industrial process. When we treat calcium carbide with water, it can give acetylene, and this ethene, acetylene is a common name, and this is a solid compound. It is a solid compound. Solid compound, when you treat with water, you can generate ethane as gas. And calcium carbide is produced from calcium carbonate. When you heat calcium carbonate, it can produce calcium oxide plus carbon dioxide. When you react calcium oxide with the carbon, you generate calcium carbide and carbon monoxide. Here involves two molecules of water. So, you can generate this is the reaction is involved. Calcium carbonate is when you heat, it produces calcium oxide, and this calcium oxide, when you react with carbon, you generate the calcium carbide. This, when you treat with water, you can produce ethane gas. So, how industry uses to prepare ethine. The next approach, common approach to prepare ethane is dehalogenation reactions. For example, if you have this one dihalo compound, so this when you treat this 1,2-dibromo alkane with alcoholic KOH, it's a base. So, it can remove this hydrogen, this is a base, it can remove one of the hydrogen. For example, if you remove this hydrogen, you generate let us write like this. The base can remove proton. So, in this case, the base will remove this proton. you generate the alkynyl bromide or called vinyl bromide intermediate. Once you form this one, you have to further react with a strong base. This you produce this alkene plus potassium bromide plus water. This will be the byproduct in these reactions. And so, once you form this one, the potassium, the hydroxide, the alcoholic KOH is not sufficient enough to remove this proton. Right now, you have to remove this proton. So, you have to use strong base like sodamide, and this can this now NH2. This is the base. This can remove proton. Another dehydrohalogenation, you can product. Basically, it involves two steps. First, what you have to do in this, the byproduct is going to be sodium bromide plus ammonia. So, first the alkali KOH removes one of the proton. It is actually a base. You do dehydrohalogenation, and further you have to use strong base to remove proton from this alkynyl bromide. Then you can convert into alkyne. This is another process we use to make alkynes. So far we have seen the structure of carbon-carbon triple bond, then nomenclature, isomerism, then preparation of alkynes. We have seen two approaches. One is how you can industry prepares ethane gas using from calcium carbonate. Calcium carbonate, when you heat, and it gives calcium oxide. The calcium oxide can be reacted with carbon to give calcium carbide. That calcium carbide, when you treat with water, it can produce ethane gas. And the next we have seen, if you have vicinal dihalo compound, you can treat with base. First alcoholic KOH, you can convert into vinyl halide. That can be further reacted with a strong base, then you can get the alkyne. Next, physical properties of alkyne. As we have seen in the previous classes about alkanes and alkenes, the first three members of the series, ethine, propine, butane, they are gas. The next 8 members C5 to C13, C5, HCl2, (24). They are liquid. So, next 8 members are liquid compounds. After that, all are solid compounds. Higher molecular alkynes, they are solid compounds. They are colorless, as alkanes and alkenes colorless. Except ethine, it gives a garlic odor, and the remaining are odorless. The density of alkynes, as we have seen earlier, alkane, alkyne, they are less than water, less than 1. So, they are less polar compounds. They don't mix with water very well, but however, they are well soluble in organic solvents. And if you look at the melting point and boiling point density, so when you increase the molecular weight, this also increases, as we have seen in the case of alkane and alkenes if the homologous compounds. And if you compare with alkene, and alkane show high boiling and melting points because they are linear molecule. They can stack each other very easily comparing to alkenes. Because of that, they show high boiling and melting points. So, now let us look at the chemical properties of alkynes. First, let us look at ethane. Just we have discussed the sp hybridized orbital of carbon is involved, the sigma bond formation between with this carbon and as well as with the hydrogen. In this case, if you look at this one, the sp2 sp hybridized orbital of carbon overlaps with this s orbital of hydrogen and to form the carbon hydrogen sigma bond. So, if you look at this this one, the S character is increased. If you see the alkane, it involves sp3 hybridized orbital, the CH bond formation. In the case of alkene, sp2 is involved. Here, sp orbital hybridized orbital is involved in the carbon hydrogen sigma bond formation. So, the S character is here 50%. That means the electron density, the electron whichever involved the bond formation is very close to the carbon, and the electron, in other words, the electronegativity of this carbon increases because of the S character is more in this carbon, and so the base can easily remove the hydrogen as proton when you treat with base. For example, when you treat with sodium, liquid ammonia, it can easily remove this proton. It can produce sodium acetylide. And similarly, and this also it can further react another sodium, and it can produce similarly, this also we can react with sodamide. This of course, you can react with alkyl halide, then you can couple this moiety, and this is very, very useful reaction. So, this if you compare the acidity of alkynes with alkenes and alkanes, they follow the this order. This is more acidic, just I have told you, and this involves the due to the more S character, the electronegativity of this increases, and the base can easily remove the hydrogen as a proton, and this more acidic, and this is less acidic comparing to the alkyne, however more acidic comparing to alkane. This is the least acidic among all the three hydrocarbons. These two are unsaturated, this saturated hydrocarbons. So, if you compare between different alkynes, and this will be more acidic comparing to this, because you have the methyl group, it can give electron to this system, and if you go further, this will be the least acidic. This is the more acidic comparing to this more acidic comparing to that. This is the acidity order of alkynes. So, now let us look at some of the important reactions. Addition of hydrogen. Alkynes can readily undergo reaction with hydrogen in the presence of catalysts like palladium, platinum, nickel. It can undergo addition to give alkene. The alkene can be further reduced into alkane. So, it depends upon the catalytic system. Suppose if you take alkyne and in the presence of hydrogen, if you use palladium catalyst, straight away it can be reduced into alkane. First it is converted into alkene, that alkene undergoes further reduction to alkane. If you remember the first class, I have shown you what happens. You see this hydrogen adsorbed on the surface of the finely divided the metal surface, and then your alkyne also adsorb. It makes you have the bi bond interaction can with the metal can interact, and once it is adsorbed in the surface, then the hydrogen transferred to the alkyne, and then you get alkyl metal intermediate that can be further reacted with another hydrogen, you get the alkene. Then in this way the alkene can be further converted into alkane. And so, if you use, on the other hand, you can also stop the reaction at this stage, and if you use a linear catalyst. The presence of quinoline. And what happens if the activity of this catalyst less, as soon as you form the alkene, it cannot reduce further alkene to alkane. So, it depends upon the reaction conditions. So, you want to have alkene or alkane, both can be obtained from alkyne, and using the catalytic hydrogenation reactions, where the hydrogen adds the same side of the carbon-carbon triple bond. This in addition, the reaction stereospecific we have seen during the discussion on the alkenes as well as alkanes. And also alkynes can also be reduced to alkenes with the trans stereochemistry using sodium liquid ammonia. This we have seen during the reaction of the preparation of trans alkenes. The next reaction is, so addition with halogen. Alkynes readily undergo reaction with the halogen. It can when you treat, for example, with the bromine, it can undergo addition with this carbon-carbon triple bond. You can form the 1,2-dibromoethene. So, in this case, the vicinal both carbons have bonded with this bromine. This addition reaction is an electrophilic addition reaction, and just we have seen the last class, it undergoes addition, you make brominium intermediate, then it attacks, you get this 1,2-dibromo compound. This can also further undergo reaction with another bromine, and you can have tetrabromoethane, 1,1-dibromo, 2,2-dibromoethane, you can make this compound, and this involves electrophilic addition reaction. The addition of hydrogen halide. The mechanism is similar to whatever we have seen yesterday to alkenes, and in the case of hydrogen halide, let us take propane as example. When you treat propane with hydrogen bromide, it can produce 2,2-dibromo-propane. In this case, the reaction goes via Markovnikov product. What happens? First, one of the HBr reacts. First, the formation of vinyl bromide takes place. Once you form this one, this can further undergo reaction. With another HBr. Br minus, this can react with this carbocation to give if you look at this, this is called geminal dibromide, and if you have the adjacent carbon atoms, this is called vicinal bromide, vicinal dibromide. So, first we have seen the addition of hydrogen, then we have seen the halogen, where you can introduce, you can make tetra halo compound, and next what we have seen addition of hydrogen halide. Using this method, you can make geminal dihalo compound, and both halogen undergo this reaction takes place via Markovnikov addition. The next example is addition of water. As we have seen the last class, this alkyne also can undergo addition with water, can give a carbonyl compound. Let us take this as example. Propane, when you react with water, it can undergo addition reaction. When you heat around 50 to 60 degrees Celsius, the water undergoes addition, as we have seen just now. Form this intermediate, which is not stable, it can isomerize into ketone, acetone. So, alkyne depends upon the alkyne. If terminal alkyne, it can be, in this case, it can be converted into acetone. Suppose if you take ethine, if you do hydration, you will get acetaldehyde. This is very important reaction. So, in the presence of HCSO4 and sulfuric acid, and alkane can undergo addition with water to give this enol form, which can isomerize to give the carbonyl compound. The next example is osnolysis. So, alkane can undergo reaction with ozone for example, if you react this compound with the ozone, it can undergo reaction with the ozone to give ozonide. This ozonide, when you react with water, let us take two butane. You can get this ozonide intermediate. This, when you react with the water, it can undergo cleavage to give this diketone. So, this of course, when you treat with different reagent for oxidase agent, hydrogen peroxide can be further converted into carboxylic acid. Therefore, if you have the alkyne can react with ozone to give the ozonide, that can be further reacted with water to get the 1,2-dicarbonyl compound. This is also a very useful reaction, synthetic chemistry. The last example is polymerization reaction. So, two kinds of polymerization reactions are possible with the alkyne, and one is a linear for example, acetylene undergo polymerization and certain conditions to give the polymer. This is a general formula. If you look at it, they are conjugated system. You have the double bond, single bond, double bond like this. Therefore, they are good conductors, and we can use these are less weight comparing to metals, and they use as good conductors. This is an example for linear polymers, and also they can react to give cyclic compound. For example, when you react together to give benzene. This is very important example to convert aliphatic compound to aromatic compound. For example, if you take this the alkyne, when you around 600 degrees Celsius, they can undergo trimerization to give benzene. This is very useful reaction to make benzene derivatives and to make the corresponding compounds, which is useful in dyes and other application parts. And instead of simple ethane, you can also use for example, propane. Suppose if you heat this compound, they can also undergo trimerization under these conditions. To give this trimethyl substituted benzene. This is very useful reactions. So, let us summarize whatever we have studied today. So, first we have seen the structure of carbon-carbon triple bond, the nomenclature, isomerism. Then we have seen the preparation of alkynes and physical properties, then chemical properties. In the chemical properties, we have seen the acidity of alkynes, then we have seen some common reactions. For example, and alkyne can be reduced into alkenes or alkanes, and the reaction is specific. If you want to make cis alkene, you can do hydrogenation, and using palladium Lindlar catalyst, you can make cis alkene. If you want to make trans alkene, you can use sodium liquid ammonia. Yesterday we have, in the last class, we have discussed about the mechanism. It goes via single electron transfer reactions. And on the other hand, if you use like finely divided palladium, platinum, nickel based catalyst, the hydrogen can further react, undergo addition with alkene. That catalyst is more effective comparing the Lindlar catalyst. The alkyne can be directly reduced into alkanes. Next, we have seen the addition of halogen, and alkyne can undergo reaction with two molecules of halogen can give the tetra halo compound. And it can also undergo reaction with hydrogen halide, for example, HBr. It goes via electrophilic addition reaction, and it follows the Markovnikov rule. You can get geminal dihalo compound. For example, if you add hydrogen bromide, you can get both, you can add both bromine atoms on the same carbon atom. For example, if you take propane, you can get 2,2-dibromopropane. It is a very useful reaction. Then we have seen hydration. It can also like that reaction with hydrogen halide, it can also undergo addition with water, is also electrophilic addition reaction. It follows a Markovnikov rule, and you can convert into carbonyl compound, and it depends on the substrate. You can get aldehyde or ketone. This reaction is usually carried out at moderate temperature. Then we have seen osnolysis. You can also convert alkyne to dicarbonyl compound, and you can the alkyne undergo addition with ozone. You form the ozonoid that can be further reacted with the appropriate reagent to get the respective compound. And for example, if you treat with water, you get the dicarbonyl compound, and if you use hydrogen peroxide, it can be further cleaved into get dicarboxylic acids. And the last part of the lecture we have seen, and this the ethane is very important compound to make new organic compounds and materials. And we see this is industry produces ethane from the reaction of calcium oxide and carbon. So, the calcium oxide can react with carbon to generate calcium carbide. That calcium carbide, when you treat with water, it can give the ethane gas, and this is a very important precursor for various organic compounds. And this, for example, it can make linear polymerization. It can give the conjugated polymers, which is very good conductor, widely used for various applications. And you can also, this is weight, they have light weight comparing to the metals. And then we have seen also they can also undergo trimerization to give benzene and the related compounds, which are also very important in dyes and other aromatic compounds in pharmaceutical industries. With this, I conclude my lecture. Thank you very much.